Hello everyone. In this video I'm going to be talking about organic chemistry. We're going to be starting a lecture on organic chemistry. Hopefully it leads us to something beautiful, a complete lecture note on organic chemistry. Okay, so here we are going to be looking at definition of organic compounds, uniqueness of carbon, hybridization of carbon, pi and sigma bonds, properties of organic compounds, homologous series, and functional groups. Okay, so that leads us to the definition of organic compounds. Now, from what we see here, organic compounds are compounds that contain carbon as their principal element, usually combined with hydrogen. Okay, usually combined with hydrogen, and may also include oxygen, nitrogen, sulfur, phosphorus, or halogen. That's a very sweet definition of an organic compound. Okay, so here we see some examples of organic compound like methane, ethanol, glucose, benzene, acetic acid, or what you call carboxylic acids. Okay, and the common sources. Organic compounds, actually the word organic means it is coming from a living source. Okay, so you have plants, you have animals, you have microorganisms, you have fossil fuels, yeah, natural gas, coal tar. Those are the common sources of organic compounds. Okay, now but there are exceptions. Now, even though carbon compounds are organic compounds, but not oxides, not carbon 4 oxide, not carbon, this is carbon 2 oxide here, carbon 4 oxide, not carbonate, not triazocarbonate 4 acid, not carbonate at all, not a cyanide. Okay, these ones are not organic, so those are the only exceptions. So you can even say that organic compounds are compounds of carbon with the exception of oxides, carbonates, and cyanides. That's important. Okay, so and that is it for that one. Now the next thing we talk about is the uniqueness of carbon. Now organic compounds are very numerous. We have hundreds of thousands of organic compounds, and that's simply because of the unique property of carbon. Now one of them is the tetravalency of carbon. Okay, so carbon has, one of the uniqueness of carbon is that carbon is tetravalent. It can form 4 covalent bonds. Okay, that means it allows it to bond with different atoms simultaneously, creating structural variety. Okay, so that tetravalency of carbon actually can form up to 4 bonds. Okay, and the next reason is the catenation. Catenation is the ability to form long chains, branch chains, closed chains, right? And carbon is the only element on earth that has the ability to catenate. Carbon chain can be as long as even up to 1,000, as amazing as that. Okay, only carbon. The only element that comes close to it is silicon, but silicon cannot form a chain of more than 3 like this, but carbon can form chains up to 1,000, can be 2, 3, 4, 5, 6, 7, 10, 1,000, and so on and so forth. So that's what makes carbon very unique and organic compounds very numerous. Now the third is multiple bonds. Carbon can form multiple bonds with itself and with other elements. For example, you can have carbon-carbon single bond, you can have carbon-carbon double bond, you can have carbon-carbon triple bond. Now, not only with itself, it can also form the same with other elements like carbon hydrogen, like carbon oxygen, like carbon nitrogen, and sometimes can even be double or triple bond, and so on and so forth. So this is another thing that makes carbon very unique and organic compounds very numerous. Another is the small size. The small atomic size of carbon makes it form very strong covalent bond. Or you can put it this way, that the covalent bond formed by carbon is very, very strong. Okay, very strong. So that's another reason. Then of course, the ability to isomerize, as isomerism. The same molecular formula can give rise to different structural arrangements, isomers, multiplying the number of possible compound enormously. So isomerism is also another reason why you can have, for example, plastic. Have you seen that we have different kinds of plastic? Plastic has a source from organic compounds, so you can see that we have different types of, these are just different isomerization, different different ways of combination that produces different types of plastics. That's very important for us to know. Now here we talk about the hybridization of carbon. Okay, and from what we see here, you can see that first of all, the hybridization is a mixing of atomic orbitals, okay, of similar energy to form new orbitals. Okay, so orbitals of similar energy can actually combine. Now let me say this. For example, um, the electronic configuration of carbon is the sixth element in the periodic table, is 1s2, 2s2, 2p6, 2p2, right? So if I want to draw the orbital diagram, it's going to look like this: 1s2 here, 2s2 here, then 2p2. Now if you notice here, this is what we call the ground state of carbon. Ground. Now you must have heard ground state. Okay, this is the ground state of carbon. Now if you follow this orbital diagram, you will notice that carbon will be divalent, can only form two bonds because there are two unpaired electrons. Unpaired, two unpaired. This is not paired, this is also not paired. Okay, now for carbon to be able to hybridize, or for carbon to be able to form four bonds, okay, it must hybridize. Hybridization is when two orbitals of the same energy, like this 2s2, 2p2, they come together as one. But before that, there will be an excitation. That's why when you're asked to write the configuration for the excited state of carbon, it has to be 1s2, 2s1, 2p3, or you put it this way: 1s2, this s now, 2s is 1, then the 2p now is now 1, 2, 3. That means one electron here has jumped and entered, filled in this orbital, making carbon have four different unpaired electrons. Then these 2s and 2p, they will join together as one. This joining together as one is what we call hybridization. It makes sure that we have four bonds ready for bonding around carbon. Are you getting what I'm saying? So there are different ways this hybridization occur, and there are different hybridization that carbon exhibits. We have the sp3 hybridization, we have the sp2 hybridization, and we also have the sp hybridization. Okay, now very simply put, in the sp3 hybridization, one s orbital is combined with the 3p orbital. That's why we call it sp3. S, p1, px, py, pz. This is what we call sp3 hybridization. And any carbon exhibiting sp3 hybridization has only single bonds around it. That's important for you to note. Whenever a carbon has sp3 hybridization, it has only single bonds around it. Okay, so once you see this, you know that this carbon here is sp3 hybridized. Very important, sp3 hybridized. Okay, now in the case of sp2, s orbital combined with only 2p orbital. That means you have s, you have px, you have py, like this. Okay, then the pz remains unhybridized. Okay, and I'm going to explain what this is. Unhybridized, un hybridized. Okay, and the way you know a carbon that is sp2 hybridized is that it will have a double bond. This unhybridized orbital goes to form a double bond, which is usually a kind of bond we call a pi bond. We call it a pi bond. Every other bonds are called sigma bonds. We are going to be looking at that later. Okay, but this forms a pi bond. So a double bond means that the carbon is sp3 hybridized. Please don't forget that. Okay, then in the case of sp hybridization, the carbon must have only single bonds. You must have a triple bond, and it's very important for us to note there. That means in sp, one s orbital combined with the only one p orbitals, and the remaining two p orbital, p, y, and pz, remain unhybridized, and they go ahead to form double bonds, which we call pi bonds. Okay, that's by the way. So it's important. Carbon, sp3 hybridized carbon has only single bonds. sp2 hybridized carbon has a double bond. sp hybridized carbon has triple bond. So if you are given a structure like this, let's say I have this, something like this, C and this, just this, and they say what kind of hybridization is found in this compound. It's very simple. This carbon here has triple bond, so this carbon is sp, This carbon has triple bond. This carbon is also sp. This carbon has only single bonds around it, so this carbon is sp3. Okay, if there is a double bond, then that carbon is sp2. Kindly note that. So in an exam situation, I will say that the types of hybridization in this compound is only sp and sp3. Okay, that is very, very important. And I want to also say this, that the hybridization can also help to shape the bond, okay, to give the shape of the compound, and that's exactly what we have here. So sp3 hybridized carbon, usually the shape is tetrahedral and the bond angle is 109.5. An important thing to note, for sp hybridization, the shape is trigonal planar and the bond angle is 120 degrees Celsius. Okay, important to know. And but for the sp, if you notice, is straight, is linear, and the bond angle for linear shape is 180 degrees. Very, very important for us to know. So that is it about hybridization. Don't forget, I started earlier by saying that carbon cannot hybridize except it is excited, and I've given you the configuration for the ground state and the configuration for the excited state. The excited state sometimes can even be written as 1s2, 2s1, 2px1, 2py1, 2pz1. You can also write it that way. That's also correct. Okay, so that leads us to the next. We talk about sigma and pi bonds. I already mentioned that. Okay, I'm not going to bother so much here, but from the previous page, I showed you guys that sigma bonds are formed by hybridized orbitals, while pi bonds are formed by unhybridized orbitals. So whenever you see single bonds, only single bonds, all those single bonds are sigma bonds. But whenever you see a double bond has one sigma bond and one pi bond. And if you see a triple bond has one sigma bond and two pi bonds. So two pi bond, a triple bond must have two pi bonds and one sigma bond. A double bond has one pi bond and one sigma bond. I hope that makes sense. Okay, so I'm not going to waste time here because you can be given a structure and you're asked how many pi bond and how many sigma bond. Okay, let's say we have something like this: CHH double bond, C triple bond, CH, like this. And you're asked how many sigma bonds, how many pi bonds. That's very simple. I will come here. This is sigma. This is sigma. This one here is sigma. One is sigma, one is pi. This is sigma. One is sigma here, and we have two pi here. Then this is sigma. So if you count the number of sigma, it's going to be 1, 2, 3, 4, 5, 6. So we have 6 sigma bonds, and for the pi bond you have 1 pi here and 2 pi here, making it 3 pi, and we have 3 pi bonds. So this structure has 6 sigma bonds and 3 pi bonds. I hope that makes sense. Okay, so here now leads us to the properties of organic compounds. So there are certain properties that are general to organic compounds and very important for us to note. Okay, one of those properties is that an organic compound, number one, is that generally they have low melting and boiling points. Very important. Organic compounds generally have low melting and boiling points, and most of them are gases or liquids at room temperature. Okay, and in case you're asked, the property that affects the boiling point and melting point of organic compound is called van der Waals forces. We call them van der Waals forces. All organic compounds are affected by van der Waals forces, and this van der Waals forces is affected by two things. Two things are responsible for van der Waals forces. One of them is the molecular mass. That means the higher the molecular mass, the more the van der Waals force. Then while the other is the branching. Okay, so it is seen that straight chain compounds have higher boiling point than branched chain compounds. That's quite important for you to note. Okay, then the second factor that affects boiling point in organic compound, but not for all of them, is what we call hydrogen bonding. And not all organic compounds exhibit hydrogen bonding. Compounds like ethanol, compounds like carboxylic acid, they exhibit hydrogen bonding and makes their boiling point much higher than normal. So whenever you are told that an organic compound has a much higher boiling point than normal, Just know that the reason is because of hydrogen bonding. But generally, it is van der Waals forces. But some of them, especially, have hydrogen bonding. Hydrogen bonding happens whenever you see a compound where oxygen is directly bonded to either fluorine or bonded to, sorry, hydrogen is bonded to either fluorine or bonded to oxygen or bonded to nitrogen. So a compound where you see hydrogen bonded to these three highly electronegative elements, that compound exhibits hydrogen bonding. Those electronegative elements are fluorine, oxygen, and nitrogen, and that's very important for you to note. Okay, and yeah, so like if you have ethanol, this is the structure for ethanol. This is ethanol, CH2, then here we have OH, you see. So you can see this OH here, hydrogen is bonded to oxygen. So this kind of compounds, their boiling point is higher than normal, is higher than what is expected of their molecular weight. Okay, and the reason why it is like that is because of hydrogen bonding. Please note that. Now secondly, organic compounds have poor electrical conductivity, and most of them are non-electrolytes. Kindly note that most are non-electrolytes. Okay, now the third one says that they are generally insoluble in water, okay, but soluble in organic solvents. So many of them are not soluble in water, but they can be soluble in organic compound hates water. That's why petrol cannot mix with water, kerosene cannot mix with water. Okay, the next one says that most are flammable and burn in air to give carbon dioxide and water. Okay, so most of them are flammable, they are highly flammable, and they can burn in air to give either carbon dioxide and water. All organic compounds you can see around you, your foam, paper, many plastics, many of the things you have around you in your wood are all organic compound. And one of the things you will note about them is that they easily catch fire, they are flammable. Okay, the next one is that they usually have distinct odors. Okay, and the next one is that they are volatile, they evaporate easily due to weak intermolecular force. This weak intermolecular force is what we call the van der Waals forces. Is the reason why they are volatile, they can easily evaporate. Okay, that's very important. We are not going to say much about the chemical properties until we get to each of the compounds. Okay, so that will be it. Now the next one is homologous series and properties. Now when we say homologous series is the family of organic compounds that have the following characteristics. Okay, it's easier for me to say that, even though here it is written that homologous series is a family of organic compounds that have the same general formula, similar chemical properties, show gradual change in physical properties, with each successive member differing by CH2 unit, which is 14 mass unit. That's the atomic mass is 14. So you can see that definition already embodies it. So I prefer to define mine this way, that homologous series is a family of organic compounds that have the following properties. The first property is that all of them have the same general molecular formula. For example, alkanes have this formula, CnH2n plus 2. Alkenes have this formula. They all have the same formula. Okay. Now secondly, each of them differ by CH2. So each of is a family of organic compound, and each member of the family, the difference of each member is CH2. Each successive member has one more CH2 group. Molecular mass, this CH2 is 14. If you calculate the molecular mass, it is 14. So you can say each successive member has one more CH2 group. Okay, molecular mass increases by 14 as you go down the group. That's important for you to note. Example is methane. Methane is CH4. Ethane is C2H6. If you look at the difference is 1 carbon and 2 hydrogen, and it continues like that. Now, similar chemical properties. All members react the same way. Some functional group determines reactivity. Okay, so all members of the same the same homologous series have the same similar chemical properties, and they have the gradual change in their physical properties. As you go down the group, the physical properties changes little by little as you go down the group, and they can be prepared similarly. That means they have similar method of preparation. So members of the same family also have similar method of preparation. And I'm going to add one more here, is that they have same functional group. Same functional group. So all members in an organic compound, they share the same functional group. We are going to be seeing in the next class what functional group stands for. Functional group is just atoms or group of atoms that gives chemical identity to a particular family, to a particular homologous series. Okay, and they also determine the chemical reactivity of that compound. Functional group is what determines or tells us the kind of reaction that an organic compound can undergo. I hope that makes sense. Okay, so that leads us to functional group. Now you can see a functional group is an atom or group of atoms in an organic molecule that is responsible for the characteristic chemical reaction of that compound. I already mentioned that to you. Okay, and we have many of them, but for the sake of your exams, for the sake of your level, we are going to be looking at about 14 of them. We have alkanes, for example. Alkanes only have single bonds, only attached to hydrogens, and the general formula for alkane is CnH2n plus 2. Okay, and they are hydrocarbons, and example is methane, CH4. Okay, later I'm going to be giving you example of the families. Okay, and for alkenes is a double bond. The functional group is a double bond, and the formula for alkene is CnH2n. Like I said, I'm going to be showing us how to use that. Then we have this. Okay, so alkyne, an alkyne with a triple bond. So once you see a triple bond, it is an alkyne, and this is the formula for alkyne, and an example is ethyne. Then you have alcohols. How an alcohol is OH. There's an OH group, so you can see the formula CnH2n plus 1 OH. You see that? Now you have aldehyde. How aldehyde is CHO, and the general formula is RCHO. Now this R is the same thing as CnH2n plus 1. Okay, this R is actually called alkyl group. It's a group, it's not a compound. It must be attached to something, and the formula is CnH2n plus 1. I'll be talking more about that in my next video. So aldehydes, and you have this. You have ketone. Ketone is CO. Okay, so that's why you have RCOR. So if I draw like this compound now, CH3, CH2, CO, CH3, you know that this compound is definitely a ketone because of the presence of CO. Ketones are also called alkanones. Aldehydes are also called alkanals. Okay, we call them alkanals. Very important. While these ones are alkanones also. So we have carboxylic acid. Carboxylic acid, it with COOH, and the formula is RCOOH, and a good example is ethanoic acid. So we have ester. Ester is known with COO. Okay, like RCOOR. Very important. Look at an example: CH3 COO C2H5. Very important. Then we have ether. Ether is known with oxygen, and you have alkyl group by the side, ether linkage, so like ROR. So you can see this formula now. This diethyl ether, C2H5 O C2H5. So anytime you have oxygen in between two alkyl groups, you know that is an ether. So we have amine. Amine is NH2. That's the functional group. See an example here, CH3NH2. So once you see an NH2, you know it is amine. Amide, CONH2. Okay, very important. CONH2. Okay, now the rest, you have nitrile. We call it cyanonitrile. Is CN, like RCN. You get that? Then we have haloalkane or halogenoalkane. I call it alkyl halide. It is either you have fluorine attached, chlorine, bromine, any of the halogen attached. We call them haloalkanes. Like you have here chloroethane, chlorine attached to an alkyl group. Then we have nitro compounds, even though we are not going to be seeing much of this, but an example is nitrobenzene. Okay, so you can see here we are asked to note that the functional group determines the chemical behavior of the compound. Compounds with the same functional group belong to the same homologous series and show similar reactions. That is very, very important for us to note. Okay, Very, very, very important. So if I write a compound like this, you can guess what this compound is. Don't worry about every other thing, just look out for the functional group. You don't need anybody to tell you that the functional group is this one here, COOH, and COOH represents carboxylic acid. Now what if I have something like this, HCOO, CH2, CH3? You don't need to, once you see COO here, you know that this is an ether, an ester, sorry. Okay, and the same thing, like I have CH3, CO, CH2, CH3. The presence of CO here makes this a ketone, which is an alkanone, and so on and so forth. I hope this is helping. Okay, so this makes me come to the end of this class. It's a series, so the next video I'll be presenting more cases in the next video. Okay, so thank you very much. See you in my next video. Bye.